All right. Hey, everybody. Sorry this is coming out late. I feel like I keep saying that. Things have just been a little crazy recently. Yeah. So we will have this due next Sunday. A little bit of housekeeping. I think we had a miscommunication with office hours. I'll try again next week. Let me know if it's better for you to meet out of class or in class or whatever. I'm open for anything as long as I'm available. Also, feel free to email me any questions you may have on this. So, let's review kind of what we know first. So first, our sample mean should be a somewhat reliable estimate of the population mean. If we're doing everything right, we should be getting about the correct information, right? If we find out that the average American sleeps for 8 hours, and then we study people, we get like a sample of 1,000, then it shouldn't be a shock that the number should be about around 8 hours. But the law of large numbers will state that variability is going to decrease as the sample size increases. However, the sample mean should be close to the population mean, but will almost never exactly match it. You can think of what we were talking about earlier about flipping a coin, right? You could flip a coin a million times and you could still not get the odds flat on at 50-50. It's always going to be a little bit off. And then also to understand an estimate, to understand any sort of statistical information, we need a measure of center and a measure of spread, or a measure of variability. So a big part of this is the 68, 95, 99.7 rule. I've gone over this a couple times just to really get into this. Basically, any normally distributed data, if we look at it as a as a normal curve or a bell curve, if we take the mean in the middle and we subtract the standard deviation, that gives us one end, and then we take the mean and we add a standard deviation, that gives us the other end, 68% of that data should be between the mean minus one standard deviation and the mean plus one standard deviation. This always comes true for the vast majority of normal curves. It's just kind of a statistical fact at this point. If you spread out to two standard deviations, it's going to be 95%. And if you go up to three, it's going to be about 99.7%, or pretty much all your data is going to be between those the mean minus three standard deviations and the mean plus three standard deviations. So this rule allows us to use things like z-scores, right? Where we can say, okay, let's normalize the data, and if it's two standard deviations to the left, that's what percentage is going to be underneath that. It also lets us create estimates, right? We can say that, for instance, if we randomly selected a sample of adult American males off the street, we're about 95% confident that the mean height would be between 62 inches, which is the mean times two standard deviations that you saw here, where the standard deviation is 4, and 78 inches, which is the mean times two standard deviations. So about 95% of American males should be falling in between, 5'2" and 6'6". So what we just did was we basically created a confidence interval. We said, okay, we're pretty confident that this data is going to be between this and this. It was a really crude confidence interval. It's not particularly good for science, but it is a confidence interval. So all confidence intervals have the form of basically our estimate, whatever the mean is, plus or minus our margin of error. Our margin of error is going to be that measure of variability. It's going to be basically like what we said here, between 62 inches and 78 inches, something like that. So what does a 95% confidence interval mean? You'll hear that a lot, 95% confidence interval. Well, you can see, right, 95% is pretty cleanly two standard deviations to the left and two standard deviations to the right. Basically, if we take this info and we do a bunch of random samples off of it, let's say we have a database of 500,000, and we take samples of 100 and a sample of 100, and we look at it, well, out of all of those samples, about 95% are going to fall within that mean. So you can see here, there's only really that one thing on the right that actually falls out of the mean out of all of those. So that should be about what a 95% confidence interval should be. So here's the equation. It looks complicated, but it's not really. So the confidence interval is your x bar plus or minus your z times your standard deviation divided by the square root of your sample size. So that x bar is your estimate. And everything after that, z times the standard deviation divided by the square root of n, is called your margin of error. So that's basically what that would be. So you would report this as your estimate plus or minus your margin of error. So let's actually do something like this. So let's say, according to a government survey of 2,000 American undergraduates, the average college saving fund, also called a 529 plan, usually has about $1,577 in it. But this really varies. The standard deviation is actually $2,076. It's a massive standard deviation. So let's create a 95% confidence interval of the true amount of the money in college savings funds. So if we look at our data, our x bar is going to be 1577 from the question. Our z, well, if we think it's going to be a 95% confidence interval, let me pull something up real quick. This is also going to be attached to the lecture as well. So here we go. So I like this one. It's a little copy burned, but I like how it just gives you outright these critical values here. So you can see here, your 95% level of confidence your value here is going to be 1.96. So we're going to plug in 1.96 there. Oh, sorry. Our standard deviation is going to be 2,076. Very rarely actually gives you the standard deviation. We'll get to that whenever we get to it, how to do it without a standard deviation. And then our n here would be 2,000. So what we do here, we plug it all in. We plug in our mean, plug in our z, plug in our standard deviation, and plug in that. So if we multiply, divide, and square root all of that, we're going to end up with 1577 plus or minus 90.98. So once we figure out which two numbers are our answers, we would present our data like this. So we're 95% confident that the mean amount contributed to a contributed from a college savings fund among all undergraduates is between $1,468.02 and $1,667.98. So let's think too about how sample size changes this. So the government sampled 2,000 American undergraduates in the study. What if they only sampled 500? Well, you see here, our margin of error, well, once we do all the multiplication out, is now 181.97. It used to only be 90.98. So our margin of error has doubled whenever our sample size gets divided by 4. So our sample size, as that gets smaller, the margin of error gets bigger, which means our confidence interval gets wider or worse, either way. So confidence levels, basically where we get that z-score, can also change our confidence interval. It's a little counterintuitive, so bear with me here. Typically, statisticians only use a handful of confidence levels. 95% is going to be your most common. As the level of confidence increases, the margin of error gets bigger. So think of it like this. If someone made you guess what the average temperature tomorrow is going to be, how would your answer change with different confidence levels? Okay, give me a guess with 99% confidence what the average temperature is going to be like tomorrow. You might say, just in case you want to be really right, between 32 and 99 degrees. That's going to be incredibly likely. But if you're asked, okay, what about less confidence? What about 70% confidence? You could say somewhere between 65 and 85 degrees. So as less certainty is expected of you, you can give closer guesses. But as more certainty is, or yeah, sorry, as more certainty, well, you have to spread out your guess a lot more. Okay, so that was pretty much it for confidence intervals. We're going to move on to our first test of significance, the one sample t-test. So the confidence interval is used to estimate our parameter, our population mean. So the one sample t-test, this new thing, is designed to assess the evidence provided by the data to support a claim about the population. So before we continue on, let's talk a little bit about the null and the alternative hypothesis. So you might remember this from back in the fall. The null hypothesis, abbreviated the HO, is the assumed answer we're trying to test. Well, this is the basic assumption that two things are not different, aren't related, whatever the opposite of what we're trying to test is. Well, the alternate hypothesis, the HA, is the alternative. It states that there is a difference, that two things are related, different, whatever we're trying to test. So, apologies for all the text, but Professor Brent is conducting a study of the caloric intake of crumble cookies. He's concerned that the caloric intake exceeds that of similar cookies. He studies cookies from competing companies and finds that the average cookie contains about 500 calories per 150 grams. 150 grams is about the average size of a crumble cookie. His hypotheses are, well, our HO is that the mu, or the mean, is going to be equal to 500, and the HA is going to be greater than 500. Note here that I'm trying to see if the crumble cookies have more calories than the average. Anytime we're trying to study to see if our mean is greater or less than something, that's called a one-tailed test. That's really important for just a little bit, just a little bit. If we're trying to see if it's different, that's called a two-tailed test. Additionally, remember here, your null statement is always going to be a statement of equality. So we're either going to have equals, less than or equal to, or greater than or equal to as your HO symbols. So going back to the one-tailed and the two-tailed, you can see here, if we're saying less than, it's going to be all the way over here on the left. If it says greater than, it's going to be over here on the right. And if it's two-tailed, if it's just this thing is different, it's going to be both sides. All right, so here's the test statistic. It's going to be x bar minus the null mu, divided by your standard deviation of the population, which is also divided by the square root of n. So if you remember our z-score equation, this is pretty similar. That's the estimate divided by the population mean, the estimate minus the population mean divided by standard deviation. The only difference here is that you're using a sample mean, so you're dividing your population standard deviation by the square root of your sample size. So as that sample size changes, so will that standard deviation. Once you find your z statistic, so you'll use the z table to look it up. Remember here, though, that every z-score table measures everything to the left of your z. If your data is trying to measure everything to the right of your z, if you're looking at what's greater than your z, you're going to have to take your z and take 1 minus the z, basically saying, okay, if this is on the left, what all's on the right? So if you're doing a two-tailed test, if you're not looking at greater than or less than, but different from, not equal to, so do that same 1 minus z and then double the result. All right. So Professor Brent's curious to see if people born in Gen Z have different patterns of phone use than other age groups. He finds data that shows that the average American spends 2.45 hours on their phone per day, with a standard deviation of 1.8 hours. He takes a sample of Gen Z phone users and finds the average phone user spends 3.45 hours on their phone per day. So our HO is going to be that the mu is equal to 2.45, And you can see in our question, our ha is going to be mu is not equal to 2.45. So you can see here our x bar is going to be 3.45. The mu of the null is going to be 2.45. Our standard deviation is 1.8. And our n is going to be 50. So we plug all of that in the equation, and we get 3.92, 1 divided by 1/4. So let's look at the table of critical values. And 3.92. Uh-oh, just realized our chart doesn't go to 3.92. So I go ahead and plug that into a little calculator, and our z-score of 3.92 leads to a p-value of 0.999996. So this is for everything to the left of the curve. So what we need to do is do 1 minus that number, which gives us 400 thousandths. Because this is the two-tailed test, let's multiply it by 2, which gives us 800 thousandths. So our p-value is way below our p-value that we typically use of 0.05. This means we reject the null. If our p-value was 0.05 or higher, we would not reject the null. Rejecting the null language, we usually say because the p-value is below the threshold of 0.05, we reject the null. There's convincing evidence to prove, and then you basically restate your alternative hypothesis. If we were not going to reject the null, we would say because the p-value is above the threshold of 0.05, we do not reject the null. There is not convincing evidence to prove that, and then we state our alternative hypothesis. So that's going to be it for today. I tried to do a little bit less this time, just so it makes a little bit more sense. This is kind of getting into the deeper side of the stats. So let me know if you have any questions, and then otherwise I will talk to y'all later.